Hello, welcome to my channel. This is welcome to Rehandran. Today, I, in this video, I'm gonna discuss about RLC response, a very important response. It is studied in almost every field of electrical engineering. It is needed in every important circuits and systems. So let's get started. So first let me draw the circuit diagram. So in this first video, um, I'm gonna discuss about source free series RLC response. So a source free series RLC circuit. Source free means there's no input in the circuit. So this is a source free RLC circuit. So this is R, this is L, and this is C. So considering initial voltage in the across the capacitor, initial current through the inductor. So in time domain analysis, in TDA, in time domain uh, where we will do the time domain analysis first. So this is an RLC circuit with no source, and this is an LTI system, and a RLC are linear components given certain conditions, and LTI systems abide by superposition principle. That's why we can apply KVL KCL very easily. And in time domain, LTI system generates linear differential equation with constant coefficients, and because there are two dynamic elements L and C, it will generate linear differential equation of constant coefficients of second order. So so let me apply KVL for the loop current IT. So by KVL, so we know that um, so for the loop current, so when current is going through the inductor, voltage is L by dt IT plus, so current through the inductor, so R IT plus current through the capacitor, which is 1 by C integration IT dt equals 0. So this is a source free circuit, so there is no input, so it's uh, 0 input. Now let us replace the differentiation with um, linear differential operator. So let me write it here. So d by dt is d, and integration dt is 1 by d. So this is called linear differential operator. We can only use it for the linear differential equations. So this will give us LD plus R plus 1 by CD, taking the IT common out, equals 0. This is this. Now we are left with d square plus r by l d plus 1 by lc current, loop current equals 0. So this is the l- second order linear differential equation with constant coefficients. So these are r, l and c are constant coefficients. So now we are gonna solve this and see what the response of the circuit is, what the source free response of the circuit, of the RLC circuit is. And this is series RLC circuit, and this is the time domain equation for this circuit. This is the linear differential equation with constant coefficient of second order for the series RLC source free circuit. Now we are gonna solve this differential equation. So we know that for linear differential equation, and we are using the linear differential operator obviously. So all the formulas for the linear differential operator will be used here, which is very convenient and easy, and less time consuming also when analyzing the circuit in time domain. So we know that for linear differential equation, total response is, so total solution is complementary solution or complementary function plus particular integral. So complementary functions are the transient response for a system, and particular integral of the solution to the differential equation is the steady state response for the linear system. So the complementary functions describe the internal networking or internal state of the system regardless of source is present or not, and particular integral is that solution of the equation where the input is present in the system. So here, because there is no input, so particular integral is 0. So particular integral here is 0, so we don't have to derive the particular integral. We only have to focus on finding the uh, complementary function and finding the solution. So we are gonna only have to find where we only have to find the complementary solution. For the complementary function, we know the characteristic equation. So complementary function tells us about the internal structure or networking, internal state of the system, linear system, so which is expressed in mathematical terms by the characteristic equation. So for the series RLC source free circuit, the characteristic equation is d square plus r by l d plus 1 by lc equals 0. This is the characteristic equation. Now we only have to find the roots of this characteristic equation, which is also called the eigenvalue, and from the eigenvalue we can find the complementary solution of this system, uh, hence the transient response of the circuit. So this is a second order uh, equation. So we are gonna straight use this formula, um, where a for second order polynomial, so ax square plus bx plus c. So root of this second order is minus b plus minus b square minus 4ac by 2a. This is the general mathematical formula for finding root of second order uh, second order algebraic function. So here d1 and 2 is minus r by l plus minus r by l squared minus 4 dot 1 1 by lc by 2 dot 1. So now we are going to define some very important parameters to get a clean and less um, uh, less complex solution, a more clean solution. So uh, let us define damping factor or damping coefficient, which is called zeta, which is r by 2l. And consequently we from the LC circuit we know that undamped natural frequency is omega n. So omega n is 1 by root over LC. So this is the undamped natural frequency. So undamped natural frequency. So now we are going to define another new term called damped natural frequency. We're going to define this. So damped natural frequency, we are going to express this by omega d, so which is root over omega n square, the natural frequency minus the damping coefficient or damping factor. This is the damped natural frequency. Now we're gonna use these terms in this to get a more less intimidating, less complex solution, or the less complex root. So say 2r by 2l plus minus root over 4r by 2l square minus 4 1 by lc by 2. So if you take the 4 out from the root, it will be 2, and this will be minus zeta plus minus root over, so the 2 will cut out. Okay, so if we take the 4 from the root, it will be 2 and 2 common out, will be cut out by 2 in the denominator, so leaving only zeta r by 2l, which is damping coefficient for the series RLC circuit, and this is square minus omega n squared. So d12 is minus zeta plus minus j omega d. So you can see what I have done here. So these are the two roots or eigenvalues. So d1 or lambda 1 is say zeta plus j omega d, and d2 or lambda 2, you can say eigenvalue minus zeta minus j omega d. So these are the two roots, and thus we are gonna get to our solution. Now what we're gonna do is we are gonna find the transient response of this RLC circuit, or the solution for this differential equation. So it is, say, arbitrary constant c1 exponential, so lambda 1 t plus c2 exponential lambda 2 t. So we know that the complementary solution is obviously complementary CS complementary solution is the summation of CII equals to 1 to n exponential lambda it. This is the complementary solution for if roots are I equals 1 to n, then complementary solution is the summation with the in arbitrary constant. So we have found two um, two roots, so the complementary solution will have two parts. So this is the um general response of the source free series RLC circuit. So far so good. Now we have designated that initial current through the inductor is IO, and voltage, initial voltage across the capacitor is VO. So we want to find the arbitrary constants now. So let me first take this by Euler's formula. We are gonna break this exponential term, and so c1 is c1 e to the power lambda 1 is minus zeta plus j omega d t plus c2 exponential minus zeta minus j omega d t. So if we take the exponential minus zeta t common out, it is common in both terms, and now if we just rearrange this further, say exponential minus zeta t, so here C1 plus C2 cos omega dt plus j C1 minus C2 sin omega dt. Now minus 0t. So let us replace this term C1 plus C2 by C3. So C3 cos omega dt plus C4, let us replace j C1 minus C2 by C4 sin omega dt. So this is the rearranged final form of the response. This is our solution, mathematical solution for the series source free RLC circuit. Now we want to find the arbitrary constants. So we know that we have defined, or we have assumed that initial current through the inductor is IO. So at t equals 0, so I t, so initial current, loop current, so it equals 0 is IO, which is, if we just plug the values, so C3 cos 0 t equals 0 plus C4 sin 0 exponential 0, so which will give us, so cos 0 1 sin 0 0, so C3 is initial current. That was really easy. Now, so now we're gonna find the second arbitrary constant. So we have assumed initial voltage across the capacitor. So for the loop current IT through the capacitor, so voltage VC across the voltage across the capacitor is 1 by C integration IT dt. So you see, this integration is quite very it's quite long and very complex. So okay, let's do it. So let us first let us define this. So let us define I, this is integral, not current, it dt. And also there's two components. If we observe this, so we have to use the integration of u v dx. The formula for this is u v dx minus du by dx v dx dx. This is very long, so let us assume u equals c3 cos omega dt plus c4 sin omega dt, and v equals exponential zeta t. So after the calculation, basically this is what we have found. So this is the main integral I with this coefficient here, and this is the result. Now we're just gonna use this in the voltage and find the C4. So we saw that the voltage across capacitor is 1 by C integration it, the loop current, the current response, it dt. So this integral was assumed I by us, so we're gonna just apply this I, um, the value we have found for the I integral here, and see the response. So at t equals 0, initial voltage is VO, so 1 by C, and I is, so I'm writing this literally. uh, so here C3 is IO, we know that. So minus IO minus omega d by uh, zeta C4 cos 0, and this term C4 plus omega d by zeta C3 sin omega dt, this is plus C4 plus omega d by zeta C3 sin 0. Okay, this is what we have found. So 1 by C, so zeta cuts out the zeta, so zeta by, so if we break this omega d, so we will find that uh, zeta square plus omega n square minus zeta squared, and basically minus io minus omega d by zeta c4. This is what remains. So this is sin 0 is 0 and cos 0 is 1. So this is we are left with, and we can cut out this zeta square, so leaving out omega n. So and here 1 by c, this is zeta, and 1 by omega n is, this is LC, so 1 by LC, it will be 1 by LC, so it will go to the numerator, and IO minus IO omega d zeta C4, which is VO. CC cut out. Now what we have got is minus zeta IO L minus omega dl C4. Zeta will cut out. So now C4 is minus omega dl VO plus uh, zeta L IO. So C4 is VO minus omega dl minus zeta by omega d. So now we have found our arbitrary constants. So if we just replace those, so C3 is initial current, cos omega dt minus V minus VO omega dl plus zeta by omega d io sin omega dt exponential minus zeta t. So if we just further rearrange this, so exponential minus zeta t so this is the answer where so this is the answer, the current response for the series source free RLC circuit with the initial with considering all the initial conditions. So and where omega n is natural undamped frequency 1 by root LC, omega d is damped frequency, which is root over omega n square minus zeta square, and zeta equals to r by 2l. Zeta is the damping coefficient or damping factor. It is, so I'm not deriving the voltage response. You can do it yourself, and you can also check the uh, integration part where I did uh, mm, the derivation to find the arbitrary constants. If you find any mistakes, you can tell me, and I will immediately try to check it and solve it. And basically this is the full time domain analysis in TD. So in this is the full time domain analysis for the source free RLC circuit response. And that's it. Thank you for watching thus far. And I'm trying to explain this as easily and intuitively as possible, but if you have any suggestion, you can tell me, you can reach out to me. And thank you for watching, and please like my videos, subscribe to my channel. Thank you.